I'm back here to talk about kinematic equation number 2 and how we can use this same graph to derive that equation. In order to derive that equation, you must know that the area bounded by the horizontal axis and the actual graph of velocity versus time indicates the displacement that the object undergoes over that time interval. So the displacement here, or the area here, I need to calculate the area of this shape. It is a trapezoid. You can use the formula for the area of a trapezoid. Many of us don't remember that, so I'll actually be just finding the area of the triangle and the area of the rectangle. So the area of this triangle is going to be 1/2 times the base, which is time, times the height. The height of this triangle is actually final velocity minus initial velocity. Right now I'm just going to call that delta V, just to make the algebra a little easier to deal with. So this will be the area of the triangle. The rectangle, the area of this rectangle is just base times height. The base is the value t, the time value, times the initial velocity. The height of this rectangle is v naught. So there's my two areas. And again, for kinematic equation number 2, we're gonna say, be consistent here. We're gonna say that the displacement, which we can call delta x, is going to just be the area here. So it's going to be 1/2 times the time times delta v plus the time times v naught. I just add those two areas together. And then if I understand, or I can use kinematic equation number 1 to solve for the delta v, because if I look at kinematic equation number 1, I can actually rewrite it. If I subtract from kinematic equation number 1 v naught from both sides, then I get on the left side delta v, v minus v naught is delta v, is going to be equal to the acceleration times the time. And so when I see the delta v up here, my displacement equation, I can just substitute acceleration times time, in which case I get 1/2 times the time times delta v, which I now know is the acceleration times time, plus the time times the initial velocity. And then I can just kind of simplify this a little bit. I can multiply this, that first term on the right side. I get delta x equals 1/2 times the acceleration, time times time is time squared, plus v naught times t. I can rearrange the order of multiplication just like I can with addition. And then I can rearrange this. I can again swap the terms here. Put this term in front, put this term in back. And I get delta x equals the initial velocity times time plus 1/2 times the acceleration times the time squared. Doesn't look exactly like kinematic equation number 2 quite yet, but realize delta anything is final minus initial. So delta x is x final minus x initial, or final position minus initial position. And that equals the right side, which I will leave untouched. And then I can just add the initial position to both sides. So if I just add x naught to both sides, it goes away on the right. And I am left with kinematic equation number 2. Final position x equals the initial position x naught plus initial velocity times time plus 1/2 acceleration times the time squared. And there is kinematic equation number 2. And again, you can use the subscripts if you'd like, but in this process, the subscripts do tend to get a little cumbersome. All right, so I'll be back in just a minute for kinematic equation number 3.